From Penn State University, this is Pennsylvania Inside Out, connecting communities to a world of creativity and knowledge. Here's tonight's host, Patty Satalia.
Tonight on Pennsylvania Inside Out, we continue our look at alternative energy with a look at nuclear power. For nearly 3 decades, there's been an unofficial moratorium on nuclear power in the United States. Not a single new reactor has been ordered or completed since the accident at 3 Mile Island. That may soon be changing. Proponents say next-generation nuclear power is cheap and clean and the only practical alternative to dirty fossil fuels. Critics, meanwhile, say nuclear energy is the single biggest business disaster in the history of the world and is doomed to fail again. Is there a place for nuclear power in our energy future? Here to talk about that is Dr. Jack Brenizer, Chair of Nuclear Engineering and Professor of Mechanical and Nuclear Engineering at Penn State. Thanks so much for joining us.
Good evening, Patty. It's a pleasure to be here.
After nearly a 3-decade moratorium, the U.S. Nuclear Regulatory Commission is now reviewing 4 applications for new reactors, and they're expecting 15 more by the end of the year. What's fueling this nuclear power renaissance?
Well, that's a very good question. I think what is fueling the renaissance most of all is the instability in fossil fuel prices and the desire to produce electrical power by the utilities at a stable rate and a base load application. By base load, what we mean is that we will have the reactors available online 24 hours a day, 7 days a week. And so this is one of the difficulties with other generation sources other than coal. Most of our plants are not on 24 hours a day. If you look at the gas turbines, they're used for topping and peaking, as is oil. The alternative energy sources that are in use today, solar and wind, have peaks and valleys, and of course we as a society require 24-hour-a-days, 7-day-a-week power sources.
You mentioned wind and coal. Coal right now is responsible for 50% of the electricity that's generated in the United States. Wind power, I think something in the neighborhood of 3%. Nuclear power, believe it or not, is almost 20% in the United States. How much more do you expect or anticipate producing using nuclear power?
Well, the challenge will be just holding where we're at. In order to stay at 20% with the 2030 projections, we'll have to build 50 more reactors of the size of 3 Mile Island and other 1,000-megawatt electric reactors.
To meet growing need for electricity.
To meet the growing need, just to maintain the 20% that we're now at. So the mantra that I continue to say is that we'll need every bit of electrical power that we can get from any source we can get it from. And of course, I think as a nation, we'd like to have it from clean, non-carbon emitting generation stations.
Now, despite enormous federal subsidies, including caps on liability in the event of a catastrophic or a very serious nuclear power accident, some say that it's not going to be easy to lure companies back into nuclear power construction. Just how receptive are companies to going that route?
Companies are very accepting of nuclear power. In fact, most of the utilities, 27 plants have been proposed now, and already 8 have gone in for license applications. There are 4 companies that have applied for 8 units, and we anticipate 15 more coming aboard. For example, Browns Ferry plant, which was shut down, has now been restarted by Tennessee Valley Authority. They've decided to complete construction of a plant at Watts Bar. We have several other plants being proposed. In Georgia, they have assigned a contract with the Westinghouse for 2 AP1000 plants. There's a group in South Texas that are investing money. The U.S. Enrichment Corporation has started the construction of a new enrichment plant. So I believe that that is not true. Companies are, in fact, investing billions of private dollars into this effort.
Worldwide, there are 441 nuclear power plants, and 104 of them are right here in the United States.
That's right.
Give us an idea of where they are throughout the United States, and is there a reason that the bulk of them, or a large number of them, for example, are in Pennsylvania?
Yes, they're mostly along the East Coast and the Southeast, and then with some up around Chicago, and then more out in a couple in California, a couple in Texas, a couple in Washington State. So the bulk of them are in large population areas. that require high demands of electricity, that have high demands of electricity.
So it's where the population centers
where the population centers are and where manufacturing is located. One of the things that people often forget is that manufacturing, such as aluminum reprocessing, takes huge amounts of electrical power, and you can't produce it at a diluted rate. You have to have a high concentration of power at one time. And so coal plants and nuclear plants are the large plants which supply that power on a regular basis.
We often hear the term next generation nuclear power. Explain what that means. What's different about the current set of buildings and plants that will be going on that's different from previous generations?
DOE commissioned a study a few years ago, maybe almost a decade ago now, where we looked into the future to try to decide where was nuclear power going, what should we design, what was needed. And out of that came this term Generation 4. And so as soon as they just talked about Generation 4, there had to be a Generation 1, since it's such as shipping port in the very early reactors. Generation 2 would be the vintage around 3 Mile Island at time frame, in the late 70s, mid-70s. And then Generation 3 reactors are some of the latest that were built. Some people talk about Generation 3 plus, which are evolutionary designs, but essentially the same as the Generation 2 and 3 reactors that we have now.
When you say evolutionary design, do you mean evolutionary in terms of safety precautions? What's different?
Well, like building a car. When you build the first car, it's a prototype car, and you have often many things that don't work well or don't work as well as you would like. And so you keep refining that. You had brakes, but maybe the brakes weren't so good, so you wanted better brakes, more reliable brakes, longer lasting brakes. And so by just doing evolutionary engineering, tweaking this, changing that slightly, adding an extra pump, changing the pressures, etc., you could enhance the safety, reliability, and the robustness of the components.
How do you respond to people who, despite evolutionary advances in this technology, say that with nuclear power there is no margin for error?
Well, I don't know of anything that doesn't have any margin for error, and in fact the accidents that have occurred have been very valuable learning experiences. In all of engineering, whenever a bridge collapses or a building collapses or there's some electrical problem, you learn from that and you build on that, the lessons learned. The nuclear industry has been a leader in building and lessons learned, and followed a lot of the safety techniques used in aviation. And I think that our risk analysis and best estimate risk analysis is some of the best in the nation.
We have long memories, though, when it comes to things like 3 Mile Island. In fact, you've given a number of talks about nuclear energy, and while there's lots of interest in the room, and you say lots of companies who are being lured back into building them, there's still protesters out there that you see here and there.
Well,
talk about the mood, the atmosphere.
I think the atmosphere is very positive. In fact, when we first really brushed into nuclear energy in the 70s and we were seeing the big growth in nuclear power, both through plants and through interest in other areas, I think a lot of people didn't understand what nuclear was. Now a lot of folks have interacted with nuclear through nuclear medicine, and they have come to think about nuclear and realize that this radiation, while dangerous in large amounts, may not be so dangerous, in fact may be beneficial in acceptable levels. And so I think as we gain our understanding, as people become more knowledgeable of what's going on, I think the public really understands, yes, there's a risk, but the risks are very, very small compared to most things that we do in our lives.
The United States is revving up for a nuclear renaissance. The U.S. Department of Energy projects that the nation will need 45% more electricity by 2030. Where is the energy going to come from? Many nations scrapped their nuclear expansion plans decades ago. Can nuclear power make a comeback? We're talking about that with Dr. Jack Brenizer, Chair of Nuclear Engineering and Professor of Mechanical and Nuclear Engineering at Penn State. Who are the global leaders in this? Which countries are really taking this on in a big way?
Well, the countries that receives the most recognition is France, which has almost 80% of its power produced by nuclear power. And then I would say the next largest proponent of nuclear power on a country level is Japan. Both of these countries have limited resources to produce electricity, and so they've turned to nuclear to fill that void. Japan is a particularly good example. They have essentially no gas, not much coal, and they have to import everything. So nuclear to them is a very good option. Nuclear power is a very high-density power source. You don't need much fuel to produce a lot of power, unlike coal, which is a lower density source. And so this means that you don't have as much waste in terms of volume. You don't have as much fuel to bring in terms of shipments. You don't have to have barge after barge coming in. And so it is, and as I said, it provides this long-term steady-state source of baseload generation.
I want to talk about waste in just a moment, but you mentioned Japan, and Japan is proving that these nuclear power plants can be built relatively quickly. They're doing it, I understand, in 39 months. How conceivable is that in this country?
It's very conceivable. One of the one of the challenges we created for ourselves is each time we built a power plant, we made a lot of changes, albeit intended to be improvements, but it meant that each plant was somewhat unique. In France and in Japan, what they've done is they've built to standardized designs. And so once they did that, then they could start pre-assembly of components, modular type construction. In fact, the new licensing process that is developed by the NRC and is about to be tested as they put forth the first licenses applications that you mentioned.
People are basically pre-approved.
They are pre-approved. In fact, they have certified designs, and so you submit your design as a vendor of a reactor. The design is reviewed and approved, and then the licensee picks one of those certified designs and then says, we will build it to this specification. So if you say you're going to build a Chevy, there's a blueprint for a Chevy, and you build a Chevy. And it's that straightforward. And so that means a lot of things that before were built on site and built slightly different than they were built before are now all built the same. And so that you end up with a much more reliable, a much more straightforward construction process.
So the construction part seems to have been streamlined, but what about the permanent waste disposal facility? Yucca Mountain is still not operating.
Done. We continue to wait for DOE. I just received an email yesterday saying that DOE is going to apply for its license earlier than they had originally intended, after some delays earlier than intended. And so by June, we anticipate that they will turn in their Yucca Mountain license application to the Nuclear Regulatory Commission. It will then be reviewed as if it were you submitting the license, and it will be reviewed through the federal review process, and then the license will be issued. Undoubtedly, questions will be raised. They will have to be addressed, and it'll be an iterative process.
And in the meantime, where is radioactive waste being stored?
Well, some waste, medical wastes and others, are going to waste repositories. We have several classifications of waste, low-level waste and high-level waste. Much of the waste that we generate in our medical programs and in our academic programs, etc., is shipped to low-level waste disposal sites, and there are several of those in the nation. The nuclear fuel was originally intended to be held at the power plants for only 180 days while the radioactivity present within the fuel due to the fission products decayed away, and then it was to be shipped to a permanent repository.
So it's still on site?
So now, because those spent fuel pools were only really intended to hold fuel for 180 days, most of them are pretty much at capacity, and what we've started to do is move out of those to dry fuel storage casks. And these are relatively small casks that hold several fuel elements, multiple fuel elements, up to a dozen, and they are stored on site at the nuclear power plants. In fact, the federal government is even beginning discussions about forming a federal dry fuel storage cask location while they decide what to do with Yucca Mountain in terms of the licensing process.
Now, when we look at what's happening around the world, Italy and the Philippines, they have decommissioned their nuclear power plants. New Zealand is a nuclear-free country. You mentioned Japan and France as leaders. Some say that the United States, if it wants to have some say in how this industry proceeds, really needs to be involved in a big way. What's your feeling about that?
Well, I think that's true. We were certainly the leaders in it. France is using an initial Westinghouse design that was licensed to France, and so they're really Westinghouse plants. General Electric produced the boiling water reactor, which is used around the world. So a lot of that technology that is being successfully employed around the world came from the United States. So I think we have the ability and the responsibility to take a large role in how things are done. Unfortunately, the rest of the world has moved on, and we have stayed sort of in a moratorium. And so now everyone else is reprocessing, but we in the United States decided in the late 70s that we would not reprocess our fuel. That limits what we can do, how we can produce additional fuel through breeder reactors. Other countries are doing this. I don't quite understand why we are not applying our great technical knowledge and trying to come up with better processes.
Well, speaking of spent fuel, I guess is what you're talking about, what's being done and how concerned are you as nuclear power makes this renaissance worldwide that this be used, preventing it from being used for nuclear weapons?
Well, first of all, the issue with nuclear weapons is that you have to have a very high enrichment of plutonium or uranium in order to make a weapon. Commercial grade fuel, upwards in the 90%. Commercial grade fuel is less than 5% in the United States. And in fact, in most commercial reactors, it's not efficient to run these very high enriched cores. Therefore, the idea of taking commercial reactor fuel and converting it to weapon is very unreasonable, let me say. It's not that it's impossible, it's just very unreasonable. This is not the way you would go about it. In fact, other countries who are doing so, it's not the way they're going about it. So I think that there's a very big difference between a commercial reactor and a reactor that produces fuel to be used in weapons, and that's a very important point for people to understand.
According to a recent research poll by Visconti Research, 86% of Americans see nuclear energy as an important part of meeting future electricity needs. I want to contrast that with something that Lawrence Solomon wrote in the Financial Post. He says that nuclear power is touted as clean and cheap, and he says it's neither clean nor cheap. According to him, quote, nuclear is the single biggest business disaster in the history of the world. No other technology has failed so big, so often, and so spectacularly. No other technology has needed so much help from so many governments over so long a period of time. What's your reaction to that?
I say look at the market. Look at the number of people who are deciding to buy new plants. Look at the number of countries that are using nuclear power. Look at, if you don't take a worldwide average but go to a country-by-country average, look at the countries that have large fractions of nuclear power and look at their position in the commercial market. I believe that those statements are not completely factual.
Nuclear engineering programs began at universities in the early to mid-60s. I knew a couple of men at the time who graduated with degrees in nuclear engineering and went on to do something completely unrelated. There's been a resurgence. I think Penn State and Texas A&M have one of the biggest graduating classes in 2006. Tell me what the job market is like for nuclear engineers.
The job market is the best I've ever seen it. I've joked about becoming an agent for these free agents that are going out into the marketplace. Salaries are very high, and some surveys show it at the highest of engineering starting salaries. Essentially, all students who have a good GPA can find a job in nuclear engineering. Many are going on to graduate school. We're attracting some of the best students in the College of Engineering into nuclear engineering, and it's made a tremendous turnaround in 10 years. Part of this is obviously fueled by the interest of nuclear power and the opportunities for these vendors such as General Electric, Westinghouse, and Areva to sell plants. And both the service market and the construction market will follow very shortly.
You're obviously very optimistic. What, though, do you realistically see as the major challenges yet to overcome?
Probably the major challenges will be proving the NRC licensing process works. In the past, one of the difficulties was the licensing process allowed constant delay and the way the federal regulations and state regulations were set up. It discouraged you, it in fact often prevented you from charging for the construction of the plant until the plant came online. So that meant that individual companies were holding large loans for a very long period of time. And so there will be some legislative type changes that need to happen, and there will also need to be some design tests and proving of these new materials and designs.
All right. Well, thanks so much for talking with us.
Oh, you're quite welcome. Pleasure being here.
Our guest has been Dr. Jack Brenizer. He is Chair of Nuclear Engineering and Professor of Mechanical and Nuclear Engineering at Penn State. For all of us here at WPSU, I'm Patty Satalia. Thanks for joining us. Have a good night.